See, that's why I wish like that's why I wish some of the Miniman ones were. Actually, I wish the art just didn't.
Okay, so the thing with Miniman is intended to be like easy for babies.
I know, but like the art should like I feel like there's so much that is like, hey, this is only for UMass. It's like I wish it went further with it.
Miniman is so fun though.
Discord.
Well, it's the easier photo. Yeah. The hard ones come for the real.
Well, the hard ones are.
I mean, the secret.
Okay.
I am writing an evil challenge.
Text it to me and I'll Discord it to myself.
Here's an idea for you. One person's got an Android phone, and they interact on it. It's your job to figure out what version of Android.
Oh. I mean, you get them to click a link, and then you use their user agent.
So
There's one way to do it if they've got that set up, right? Like what browser they're using. Okay, what hardware is it? Because that'll make it.
You could have in the page go into browser.
I think that's a start of a challenge.
Wait, they have it on the note.
Or it could be the fact that the person is not just kind of click on anything, but they do have something they have to do. You have to, like, their job.
Oh yeah, you have to use those like down link. I'm like, oh, yeah, and they'll totally click on it if it looks like.
Yeah, it doesn't yell at you saying, hey, this link is actually this.
They can switch up a lot.
You gotta get this. That's a reasonable.
There we go. Yeah, there you go.
Well, like, it'd be pretty easy to set up a bot.
Stay still. Yeah, that helps.
Targeting challenges.
Alright. Jade, are you gonna
Your
write
number
down?
is no, it's your
For that, I want to bounce up.
we gotta get this working.
Spend 24.8.
2 fingers at the very end.
Alright.
So yeah,
Dictionary from like 5 megabytes.
Battery on this is dying too. All my batteries are dying today, so. And there are no
Are they not the spare ones?
It does say extra battery. I'll ask you.
I did watch like 8 hours worth of videos.
there we go.
You can also just have a bunch of stuff.
It was okay. I think like
I think you can read all of that.
is that like
I just find it.
I've got it.
Anything to understand.
Okay, figure out. Because it's like, oh, like
Yeah, I mean,
you usually learn to do something like
you also look like
that's the only thing that's happening.
Yeah, just
Alright, so when some of you were here and not all of you were here, I was talking about how the homeworks are going to go from now on. Every homework, I'm going to take something away from you, and you're never going to get it back. So, man, this microphone's a problem today. I'm going to have to yell, I guess.
I'm gonna fix CS.
Find some batteries.
Yeah.
Find some batteries. So, what did I take away from you for homework 2?
You can't read the code.
What?
It's hexadecimal.
542.
Oh, sorry. It's not big enough.
oh, do you have to compare?
I was gonna take up the whiteboard space.
yes, the one
All right. So, what did I take away from you for homework 2?
source code.
You're not getting it back. You're never going to see source again. It's all gone now. Next homework, after we learn about ROP today, we're going to take away your executable stack, your executable heap, your executable.data, and your executable.bss, and you're never going to get them back again. So page protections are now going to be correct. Later on, next thing you're going to lose is probably going to be your address reliability, and you're going to miss that the most. But hopefully, once we've gone through this, it will be a lot less intimidating for you. Next Tuesday, we're going to go over the homework and midterm. I'm going to hand you the midterm. On that Thursday, we'll be in here, which is the official date of the midterm. You can ask questions. It will be due at the end of that period. And then, except for people who have accommodations, obviously, I'm sorry, they'll go into spring break, which is unfortunate, but I'm giving you 2.5 days for a midterm that's like 2 pages long. So shouldn't really need it.
Wait, are we all like having extra days for it, or is it just class for the rest?
You'll get it on Tuesday.
Okay.
You do it at the end of class on Thursday. So the Thursday period for class is the official midterm. You will have had it in your hands for 2 solid days before that comes up. All right. So we've actually seen 2 mitigations already. This is incorrect. The first one, you already walked over in exercise 2 for the homework, and that is the stack cookie or stack canary. We handed you one of those. You figured out how to hop over it. There are older techniques to bypass those, but they're not particularly useful anymore. So the idea there is that you are attacking what is on the stack, right? What you have on the way to the canary, or you're figuring out how to hop over it, or you're transitioning your bug from a stack-based overflow into something else, right? It wouldn't have mattered if there was a stack cookie or stack canary on the first homework because you didn't attack the return address anyway, right? There was no reason to write outside of your stack frame, so it wasn't a problem. So we are going to be looking at what is known as DEP on Windows, data execution prevention, and NX or write XOR X on Unix and Linux. This stuff was standard in many, many architectures. It was standard on PPC, it was standard on Spark, it was standard on some MIPS, but it wasn't on x86 because x86 was a consumer platform. It was not a research or corporate or large-scale computation platform. Long, long before your Windows or your Macs had any concept of multi-user or multiple programs or virtual memory spaces, these research machines that were seriously used in industry and research had all of this stuff already. So it was really moving it from those older platforms onto the home platforms. Those Macs that you were all using did not have any of this until 2001 or 2002. So up until that point, there's no virtual memory space on that sucker at all. No page protections. You could write over the kernel from any user process. It's great. All right, so what's going to happen now? Previously, we had this linear idea of page permissions. So you could have nothing. It could be read-only. It could be read and execute. You can't have execute without read because the processor's got to be able to read the memory before it can decide how to execute it. And then you could have read, execute, and write. So if you had write, you had everything else, which is a problem. Well, for defense, it's a problem, right? And the reason for that is because every time you add a flag to any luck? Nice. Anytime you add a flag to that page table that some of you may have read about after the first or second classes, that page table gets larger, and then the hardware that is meant to handle that has to be able to handle those flags and understand what they do and implement them. And so this became possible on x86 when they added the PAE, the address extension hardware, and then it had to be implemented in the kernel and in the loaders to handle that. And then also in the compiler had to be able to say, I want this page this way and this page that way, right? All that stuff had to jive together. It took a little while for that to happen. Once it happened, read, write, and execute, or at least write and execute are now disconnected, right? Read and execute always have to come together. You got to execute, you got to have read, okay? But now you could have write and execute separated, and you end up with the same type of deal that you have if you've ever used chmod on a Unix machine, right? Each one's got its own bit. They all mean something different. The long and short of this is that your stack and your heap and .data and .vss, all those writable sections, are no longer executable once you can split those page protections out, right? So up until now, we have been executing all of our shell code on the stack. Even when you are returning into a code page for your return address, that code page return address was still jumping you back into the stack to execute your arbitrary code, right? When I say execute arbitrary code, I mean the shell code bytes that you have passed in, right? All executable code is just merely bytes, as you have seen. And so even once we have ROP, our main goal is still to gain execution of arbitrary code. Whatever shell code, whatever assembly instructions we put in, we want to get executed. And so that's our goal here. And so there are not very many paths that you have to follow through a ROP exercise to make use of that, to be able to execute your arbitrary code. So you've seen the basic idea here, right? We've done return to lib for every single exercise you've done, right? There is no returning to the stack or hard-coded heap addresses in this class. That is a sloppy 1992 move, and we do not do it. And you've been using that jump ESP gadget. Now, I've been giving it to you in your binary. Anything in any code page is fair game because it will not move relative to the code page. Even when we have ASLR, which we will see subsequent to this after we've introduced the heap, wherever that code page is put in memory, the byte for that jump ESP or whatever gadget you're looking at will be the same distance from the start of wherever that module is in memory. And so if you ask your GDB or you look at proc map and it shows you where all of those modules are loaded, it'll give you a base address. You just do addition, right? If you open something in your disassembler as a DLL, and you use the rebase, or what is it called in Ghidra? To rebase? Is it still rebase? What's it called in Binary Ninja?
Rebase.
Rebase. All right, so in all three of your disassemblers, it's called rebase. And what it does is it says, I want you to load this module, this binary, DLL or shared object or program at this address. And so what you should probably do is load it at 0. And the reason you should do that is because wherever you have loaded it, or whatever you're looking at, whatever address it says it is, it's wherever it's loaded plus that number, right? And so it's very easy to do the math. If you rebase it to where GDB has it loaded and you're not using a snapshot, so it's being reloaded over and over again, if ASLR is on, that base address will change all the time. If you set your disassembler to rebase to 0, what you know is it's that module plus whatever that offset is. It's very easy to do. Every debugger will let you use the module as a base address. So you could say like libc plus this number, right? And it'll get you where you want to go. And when I show you some of my ROP examples, you will see that I never have, in my address tables, I never use a full absolute address. I set a base, and then everything is base plus whatever the offset is, right? Okay. So we've done the jump ESP. You also did returning directly to a function. So there's two different moves here, right? One of these is you jumped to an arbitrary place and used one instruction. This one instruction itself is a branch instruction, so it's moving directly someplace else, okay? Sometimes you'll be somewhere above that. It'll do something else and then branch, right? And so when we look at building our ROP chains, that's going to be the form of it. But returning directly into a function is just as valid. And it also gives us a benefit on x86 standard call that I will show you shortly. But I want you to be thinking about all of these things as basically the same. You are returning not into your arbitrary code, you are returning into some code that already exists on a code page that is at a predictable place. Okay. So in the scenario that we've got now, let's think about, let's use that ABO1 stack. Is this going to work for me? Oh, it is. Somebody brought us new markers. I don't know who, but bless them. RB. Is this large enough? Someone has to say yes or no.
Yeah, it's good.
Yes. Thank you. Right? And so we wrote to here, we smacked ret, and then we put our shellcode right here. So at crash time, and when I say crash time, I mean once we have overwritten something that is going to cause the program to fail if we don't fix it, EIP is going to point at an arbitrary address. So we control the IP. We control ret. We control buff. And normally we had put our shellcode right here. Okay? So that requires two things. First, we have to know what ESP is at crash time, right? We didn't get really explicit about this, but when we crash here, when we gain control of ret, before we decide, oh, we can do jump ESP, we have to know something about the state of the program at crash time. And the thing we know is that we just popped ret off, so ESP is pointing here, right? B sub 2. Right? That's the implicit thing that we know. And using jump ESP to jump to our shellcode that's written there relies on that fact. If ESP is not there, we can't do that. But ESP is not special in that regard. It just happens to be what you can reference your data from in this example. Every other example will be different, right? You will almost always have some access to your data. If your data caused the program to crash, it's probably being worked on at crash time in some way, right? Which means there's got to be someone, either the stack or a register or something else, that is referencing that data at the time. And it will be your job to figure out what that is, because that will tell you what's feasible to do when you have control of EIP, right? So in this case, we've just used, or previous cases, we've used exactly one gadget. That's not necessary. What we could do is chain multiple gadgets, such as jump ESP, together. We wouldn't want to use jump ESP in this state, but we can. And the way that we do that is we make use of the thing that directs the program flow. And what's the thing that directs the program flow?
Stack.
The stack, right? That's where ret is. And so as the stack rolls back up, it's defining what the program is going to do next, all the way back down the line, right? The instructions tell you what to do next if you're adding to the stack frame, but if you're rolling the stack frame back up, the stack itself controls the whole thing, right? In this case, we have a very simple stack control. We are already writing to the pages that make up the stack when we start, right? So all this, we control. And if we put multiple addresses here, instead of putting shellcode and jump to ESP, we just put different addresses that run different pieces of code there, they're going to get run. And I'll show you exactly how that works. Thing to note, the pages that are mapped as the stack are not the important part here. The important part is, where is ESP pointing? If I point ESP to the heap, the program's not going to care, right? It's just going to say ESP subtract, ESP subtract, ESP subtract, right? Or ESP add, right? It's only going to reference the stack by ESP. Whatever the loader thinks it mapped as stack pages, not important. One caveat for more advanced players, if you are in the kernel, it does have to point at pages the kernel has mapped under its control, meaning not the in-context user space pages. It will not like that. But apart from that, anything ESP points at is now magically our stack, because nobody's validating if ESP happens to be in those pages. You would be doing that at literally every instruction. It would be very expensive. Hasn't occurred to anyone yet. All right. So because we are working with the stack in the way that it unrolls itself, we need to be primarily concerned with how function calls get made if we are going to make function calls with our ROP chain, and we are. And so we have to be aware of our architecture and what calling convention those functions in particular require. Now, you will find a mix of standard call and fast call in a lot of libraries, and they are going to be dependent on how often those functions get called and how fast they need to be, right? Everyone has heard execute the common case fast. Raise your hand if you haven't. Where is your, nobody has ever heard the phrase execute the common case fast. All right, I'm gonna have to go to the computer science department and have a discussion. The idea is, if you are optimizing things, you don't pick the slowest thing. You pick the thing that runs 100 billion times a second. It doesn't matter if it's way faster than the slowest thing. That's where you get the bang for your buck, right? If you add 0.1, you pull 1.1 seconds off the thing that runs a billion times, or 20 seconds off the thing that runs once, 0.1 seconds is still going to win the race, right? Execute the common case fast. So what that means is the compiler is going to, or the developer of a library is going to say, man, this function gets called constantly, and so I'm going to do some trickery to optimize it. So sometimes you'll see fast call, right? Here's the difference. Standard call is what we've seen thus far. The arguments are pushed onto the stack. Everybody's seen that, right? You have also seen an example of fast call. Where have you seen an example of fast call?
Syscalls?
Yep, syscalls, right? In your shell code, everything is pushed into or moved into registers, and those are how the arguments for syscalls are made, right? Does everybody remember that? Gone through a bunch of shell codes so far. It's the same way for a normal library call. It looks just like it, and it uses standard registers in order. So it'd be EAX for the syscall number, EBX, ECX, EDX for the first three arguments. This is also how almost all other architectures take arguments for standard functions. If it goes past something like 6 arguments, if there's like 7 or 8 arguments, then you'll have 6 in registers and 2 pushed to the stack because it just runs out of registers. But most other architectures, RISC architectures in particular, tend to have a lot more registers that are not special purpose because of the architecture. So almost always you'll see fast call instead of standard call. Finally, and this will be important later on when we start looking at heap overflows and use after freeze and other heap stuff and C++, is cdecl. And what that means is that the this pointer for the class that's being referenced, this is going to happen when you call a class method only. The this pointer, right, it could be the first argument pushed to the stack, it could be the last argument pushed to the stack. This is the normal way that you're going to see it. The this pointer is stored in the ECX or RCX register for x64. Does that make sense? All the other arguments will be however normally it is. So standard call if it's cdecl. But your this pointer is an ECX. And that will become very relevant because that means, what does this tell us? What is the benefit of having the this pointer in ECX if what we are primarily concerned with is where data we control might be referenced by registers in memory at crash time?
You're like calling from a B table, if I said it correctly.
If you're calling any class method that is where you gain control of the program, ECX is going to point at data you control, right? And so you're going to very often be looking for gadgets that reference something based on ECX in order to get control of your stack, okay? So let's take a look at an example of a ROP chain on the stack in memory as it would be done for standard call. In this case, you can imagine that what you have written for ABO1 is your buffer size, and then you've written this chain immediately after that. So yeah, this address here has overwritten ret, okay? So this example is mprotect, and I'll tell you why mprotect is something you're going to want to do later. Here's the thing to note. Immediately after the function call that you're going to overwrite ret to, so imagine you've done this with system basically before, right? We're going to use any other function we like. This time it's going to be mprotect. The thing to note is the arguments are not immediately adjacent to that call address, okay? Normally when you call a function, you use the call instruction. And the call instruction does something important apart from moving EIP. What is that? If I do this, what two things is that going to do?
The one thing it does is like it pushes the next instruction onto the stack.
Yeah, right? So when you are drawing your stack, even for main, for ABO1, you've got your old EBP, you've got ret, and then you've got your arguments, right? So you're going to build that same structure here. And that means that you've got to put this ret here because we're not calling call, we're calling ret to call a function, right? So you've got to put that ret there, but that's good for you because if it wasn't the case, if this wasn't here and it was just these arguments and there was no cleanup on the function, what would happen? What would be the next thing we return to after mprotect finished if this wasn't here?
The next instruction.
Nope. It's on this,
Masked address.
the masked address, right? We would return to the argument, right? So that's great because what we're going to put here is a gadget that says add ESPC ret. So we're going to find add ESPC ret, which is like 3 bytes somewhere in any code page. So we're going to put that address here. And what will happen then is when we've called this function, we've made use of these arguments. We roll up to here, we call ret again. Ret's going to add C bytes. So we're here, 48C, and now we're at our next call. So it gives us the opportunity to clean up our own arguments off the stack. It is more complicated to do standard call on x86 ROP than it is to do fast call or any other architecture. Because on the other architectures, as you will see, while the ROP chain is longer, it's just simpler to read, right? So here's the trick on these, and you're going to have to do this in this class. So if you don't understand what's going on here, we'll have to sit down and figure that out. But standard function address, the address of a gadget that cleans up the stack.
Would you also need a full EBT, like a fake one?
No, because the preamble to the function starts with push EBP. So the function itself is going to take care of putting EBP there and removing it for us again, right? Often, though, once you've gotten to your ROP chain, you've already screwed up the base pointer anyway, so it doesn't really matter if it saves it off or not. Its stack frame will still be correct because it will always use the current value of ESP. So it'll be here. It'll be putting its locals here. It's going to overwrite what you just jumped to with its locals, right? And it's going to use the stack pointer as its new EBP. So it'll probably store off and reload garbage in the ABO1 example if you've overflowed the stack, but you don't have to worry about that. At call time, its arguments, ret gets pushed by our call instruction. That's all we're responsible for. And so that's how this works here, okay? But apart from that, here's the call we're going to make. Here's a gadget that cleans up the stack. Here are the arguments to the function we're calling, okay? And you write those straight out. I'll show you how to do that in a second, but after you've got these, the next thing is whatever next call you're going to do again. This whole thing here, you repeat it right here. And doing that, you can chain together arbitrary calls of functions. You can also chain together arbitrary pieces of functions. In this example, we are calling the start of mprotect. You could call the middle of mprotect, right? Let's say you happen to know that on the system you were attacking, somebody is using a defense product that hooks all the function calls and then asks somebody else if it's legitimate for you to use those function calls. Well, the way that they're doing that is they're putting their hook right at the start of the function. I'll show you how to write hooks later. But if you just hop past that, they'll never see you, right? You get to choose.
If you jump to the middle, then you won't get the preamble, right? So
You won't get what?
the preamble.
Correct?
Okay, so what happens when you get to the end and leave and red?
It's your responsibility to have put the EBP there in that case. If you hop over a piece of a function and you know that it's going to perform certain actions, you know it's going to perform those actions. It is your job to set up the situation so that it gracefully has what it expects, basically, right? And that's a very common thing, not just in this case, but in a lot of cases where if you are making use of other people's code, you have to set up the situation so that when it runs, it's not going to crash, right? But it's always going to run the same. You picked where you jump to. So knowing that, yeah, you can be like, mprotect, garbage value for EBP, because we don't care what's there, and then ret, right? Or you can use a gadget earlier on to give yourself a legitimate EBP, right? I could say, find myself a gadget that says, move EBP, ESP, ret, which would be a very small 2 or 3 byte gadget at the start of my chain, giving myself a legitimate EBP and working from there, right? When you are writing ROP code, it is exactly like you are writing assembly, except instead of you providing the bytes, you are finding the bytes already provided and making use of them, okay? The form that you are generally using is something you want to happen, and then ret. Because ret says, okay, now go back to the stack and do the next thing I want you to do, right? That's why it is called ROP, return-oriented programming. That is not the original name for it, but that's the name that caught on.
Just to clarify though, here, it's not a ret instruction after the mprotect, it's an add instruction, right? Yes.
Okay, so I put ret here so that people would recognize that this, when we normally draw the stack, we say ret, right? So this is the ret to mprotect. What it is actually pointing at is the next gadget, which is our add ESPC, right? So it's going to be the return address as far as mprotect is concerned. But what it returns to is what I had drawn up on the board previously. Okay, and we can chain that arbitrarily, and sometimes you have to. Sometimes you have to go all the way with this. If somebody has written a program, and this is the unintuitive piece. If someone has written a program that other human beings are running, not example to show that you understand something, not a toy problem, but a program that other human beings pay money for and use on a daily basis, it will absolutely have every piece of code you could possibly need. Because everything is built in computers the same way, the same chunks of code are always output by compilers. And for any sufficiently large module, it will have everything you need. And that is, does violence to common sense in some ways, because very often you'll be like, man, I need a gadget that does such and such. What are the odds of that? The odds are 100%. I have never in my life not found the gadgets I needed, ever, okay? You will always find them. And the reason is because they're very often extremely simple and extremely common, right? What we want to do is get to the point where we can execute arbitrary code, right? And getting to that point is not very difficult. All those pieces, you're going to have them, okay? So when we looked at that previous page, another thing that's very strange that you're going to have to come to terms with, we're looking bottom to top, right? And so our mprotect call is here. But when we are copying into memory, this is a low address, this is a high address, we copy from low to high. So in Python, when we write it, it kind of looks upside down, right? mprotect is the first thing. Here's the ret at ESPC. Here are the 3 arguments. There's our next call. So when you're writing your ROP chain out, it's actually a little bit easier to conceptualize it because you're like, what's the next thing I'm going to do? And it goes in that order, first thing, next thing, right? But when you draw it on your stack, it will be upside down to how you've written it. Okay. Does that make sense to everybody? Cool. This call is out there. All right. This is actually a fair bit simpler than our other one, even though there's more gadgets in here. Because everything we're doing is in registers, it's always going to take this form. Pop register ret, so pop EAX ret, which is just 2 bytes, the value we want to pop into it. Pop EBX, the value we want in EBX. Pop ECX, the value we want in ECX. Pop EDX, the value we want in EDX. And then finally, the address of an int 80 or syscall ret, right? Now, each of these is not just pop EBX, it's pop EBX ret. Luckily, those are very small. They're found everywhere. And because it's 2 bytes and you can misalign things, every, so ret instruction is C3. That's it. OX C3 is ret. It doesn't matter if it's actually used as a ret in the program. If the byte C3 is there on an executable page, game on. Whatever byte comes before that, we can use that as a gadget, right? And so when we get to the end of this, I'll show you how to make use of that to hunt gadgets. Does this make sense to everybody? Kind of the simplicity of this situation here, and does it look a little bit more doable than the function call version? A little bit less indirection going on. There is, however, a slight problem here. In certain cases, especially if you're looking at strcpy example, that value is 7D. That means if you're going to pop it into EAX, it's going to be 0000007D. Now, there's a lot of ways around that, and I'll show you a couple, but it is something you'll have to be aware of. So if you end up doing something like this, which you will in homework 3, I haven't decided if I'm going to give you a mem copy or a stir copy. I'll probably just give you a mem copy so it won't be a problem. But if I mean and I give you a stir copy, there are ways around that.
How exactly are we popping the values into those, like, just don't follow that.
Okay. So each of these, every single one in this page is an address to code, address to a code page, right? And so this one here is an address of this gadget, pop EAX ret. It's 2 bytes long. So I'm going to find that somewhere in the code, and I'm going to put that address here, just like I'm using the address of system, just like I'm using the address of jump ESP, like you've done. Instead of jump ESP, you're going to be looking for pop EAX ret, right? And you just put that address there. So when the code calls ret, it's going to pop this off and execute it. Now, it itself calls ret, so the first thing it'll do is it'll pop EAX off, so it'll pop this value in EAX, and then it's going to call ret. And the next thing on the stack is the address of our next gadget, right? And that one is pointing at pop EBX ret. So it is value that's going to be run, value that's going to be popped, value that's going to be run, value that's going to be popped. Does that make sense?
Yeah, so there's like 2 rets basically that's working.
There's going to be...
Like it's treating it as a...
So remember, the stack holds a lot of things. It doesn't just hold return values, right? It's used for locals, it's used for arguments. You can push and pop to and from it, and you can get return addresses from it, right? And so we're abusing all of that together to chain pieces of code and data together with that stack. And so the only reason that this is not a return address is because the code we're running, whatever it is going to pop into EAX. So it's making use of the stack, it's moving ESP, And the next instruction that's run is ret, so this is going to be treated as an address of code. The code we run there is pop EVP, so this is going to be treated like data pop to the EVP. The next instruction is ret, so this is treated as a return address. Right?
Why is a null byte in the syscall value a problem for string copy?
Because if you were to just write here 0000007D in order to pop that into EAX, you have 3 null bytes, right?
Why would the register's not wide enough?
No. The problem is you have to write this into memory. And when you write that first null
Throw a
byte,
string copy.
yeah.
Oh, okay. I thought you were saying calling.
Oh, no. I'm saying like if your primitive, your buffer overflow primitive for which you are writing this is from strcpy, it'll stop reading right at the null.
Is syscall val, is it a call or is it like value of the return of the call? Like on the stack, syscall val? Or is
Syscall here?
no. Like
Here.
Yeah.
So the way that your syscalls work, and you've seen this in your shell code, is that the value of EAX is an index into a table in the kernel. And it's just from 0 to however many syscalls there are. Take that number, walk to that index, and then use that handler to call a function. Right? That's how the syscall works. And EAX is that index. So when you call a syscall, you look up, say I want to call exec, like we did in our shell code. I pull up the table, and I walk down and look up exec, and it's B11. Right? So that's the number I have to put into EAX to get that call, which is why the shell code looks the way it does. Right? And then in order to make that actually happen, once we set up all our registers, you'll use either int 80 or syscall instruction. They both do the same thing, right? You call an interrupt, the kernel says, hey, what's EAX? Okay, go to the table and figure it out. Okay? This is how I would suggest you do your first ROP homework. If you want to use the other method, that's cool. But I think this one's a little bit simpler. And on Unix, you don't need to use libraries to make your calls. You can use syscalls. If you're on a couple other operating systems, you will have to use library calls to do it, which means you need to know where those library calls are before you start. You need to resolve them in some way, right? But on Linux, your syscall numbers will never change. When they add a new syscall, they append it to the bottom of the list. So this way is totally valid and a little bit simpler.
You say use this for the first ROP homework? What do you mean? Which homework?
Have not given it to you yet.
Gotcha.
It'll be homework 3, next one.
So when the program executes, is it called the first syscall first, and that gets popped up the stack first, or
Does it call the first syscall?
like at the very top of the stack?
So at execution time, so let's define execution time right now as when you have control of EIP, right? So normally you've pointed it at jump ESP. Instead of doing jump ESP shellcode, this is what you put there. This is what you overwrite ret with, the start of your ROP chain. And this will say, all right, I'm making use of, I'm not doing it in one go, I'm going to make use of the stack to execute all of this. And it could be multiple syscalls, could be just one, right? So this is an example of one syscall. You could take this and copy paste it and run 3, 4, 5 syscalls in a row, chaining them, right? You could store off the return value of a syscall and then make use of it later, which you will see in a memcopy example, which I believe is, oh, no, tricks for null bytes. We'll get there in a second. A lot of these things are going to have a lot of null bytes, right? A lot of the arguments to syscalls, a lot of the arguments to your functions. And so if you are messing about with strcpy primitives, that's going to be a problem for you, but there are a bunch of ways that you can get around that, okay? Some very simple math will get you most of the way there. So let me give you an example of what that might look like. All right, so one of the values we need to put in is 7D, is that right? What's our XOR operator in Python? Is it caret?
Yeah.
Okay. Well, I can't put in 0000007D, but I can put in 11111116C. And I can pop into another register, one that I don't often use, 11111111, and then all I need to do is XOR two registers together to get my value, right? Does that make sense? So my chain would then be something like, using a big marker, then my chain would be something like, pop RDI 11111111, pop EAX 11111111C, 116C, and then XOR EAX RDI, and now it's much bigger than it was before, but basically what I've done is store 0000007D in EAX, right? So that's a quick XOR example. And if you've got a lot of them, this is not bad because you do this once, and then from then on, that's all you do. And if you're doing that, I would suggest what you do is write a small function that outputs this stuff. And so you simplify your code, right? You would say store EAX, and then your argument is some number, and it will build you this chain, and then you just put that right in there, right? So you can pull it out and make it a little bit simpler for you to read by making functions that build you pieces of ROP chains, right? Does that make sense? So that's one option. Yet another option would be, let's say, op EAX 7D 111111, and then shift EAX. So that might look something like hex 1, and I want to right shift it by C bytes, which is, 24 bits, C bytes. Oh, 28. Oh. Oh, yeah, there we go. Okay. So we provided a number that's filling it with, filling the zeros with ones, and then we just shift it right, and we end up with our 0000017, right? So that's another way to do it. You can come up with any number of tricks based on the gadgets you happen to have or find quickly in order to do this stuff. But that's the sort of way that you can work around these restrictions. You could also do this if you were writing shellcode and had the same problem. You could just write that stuff straight up, right? The homework 2 example does not have a size restriction on your shellcode, so it does not have to be small or tight in any way.
There is one, but it's really big.
It's really big. It's unreasonably large. If you write so much assembly that it doesn't fit, you should know that you've probably made it too hard on yourself. All right, so we know how to write a chain. We know how to call a syscall. We know how to call a function. We know how to mess with our arguments. What do we do now? Well, the most simple thing that you can do is to make or get a read-write-execute page, put your code there, and then jump to it. Your goal is always run arbitrary code, run shellcode. And so what we need to do is we need to take where we have our shellcode and make it executable, and there are function calls to do that. or we need to make new memory and copy or read our shellcode in. Now, in some cases, you may be more limited in the space that you have. And so one thing you can do is call memcopy and then call read on whatever socket or file descriptor you have providing input in, and then read all your shellcode in to that new page. So instead of plopping this huge shellcode down and then jumping to it, your ROP will malloc a new page, or sorry, not malloc, mmap a new page with proper page protections, and then you read the shellcode into it, right? So you don't have to bring your shellcode along with you on your first go. You can get execution and then put your shellcode in, and that is called a stager. And you can write stagers in straight shellcode if you don't have enough space, or you can write stagers in ROP to save yourself space, right? So we talked a little bit about egg hunters, and there are a type of stager, basically, right? It lets you bring your large shellcode later on. So get a foothold, make more space, then read your shellcode from wherever you're getting input from the program, okay? There is a more complicated situation, though, and that is any piece of hardware that has a fully signed boot chain. Is anybody familiar with a piece of hardware like that or know what that means?
The Nintendo Switch, I believe.
Is it? I don't think it is.
I thought it did, but it was just badly written.
Well, okay, so if somebody has a fully signed chain and it's badly written, it's not fully signed chain. It wouldn't have been their intention, but it's like if somebody has ASLR, but one module is not opting in, they don't have ASLR, because you only need one module to win, right? Okay, but what does it mean to be a fully signed chain?
Like, it makes sure that basically all the code has been, like, it's from the actual manufacturer. It's, like, signed cryptographically.
Yeah. Does everybody know what a TPM is? Yeah? TPM is a piece of hardware that can store a small amount of data and perform some mathematical operations. Generally, those mathematical operations are crypto operations. And so what you store in there is a private key that can validate signatures on whatever you like and can perform the mathematical operations to do that validation without letting that key out. And the idea when you build that hardware is you build it so that nobody can leak whatever data is in that storage out. That's the primary purpose, right? And so this guy and the Xboxes or PS5 or anything where somebody wants to hand you a piece of hardware, but they want it to be theirs. Like they sell you this thing, but they keep it. It's still theirs, it's not yours. We'll use a fully signed chain. And the point is, at every stage of boot, every stage, so starting at your bootloader processor, there are like 3 or 4 processors in here that get run before your main M whatever the heck processor actually boots. And each one of those, the bootloader has a small TPM, and it says, I will only allow code pages to be mapped such that those pages, if I hash them, that hash is signed in a table, and I can validate with my private key that that has not been tampered with. And so what that means is it doesn't matter if I have control of something in the middle of that chain, or I flash firmware with custom firmware halfway through the chain. When the lower processor boots up that main processor, it will validate that I have not monkeyed with those pages, and it will stop booting, right? And so what that means is they get to control what is executed on here at all times. Now, there are generally trade-offs made for speed with things like just-in-time compilation of Java. For the longest time, there was no JIT on these at all. And so when they were first owned, they were owned by glitching. And that is when you apply electricity randomly to the bus to flip the page protections that we just talked about at the start of this lecture. Right? So each of those, when processor talks to the memory, it talks over the bus. Those are pieces of copper. And you just electrocute them until you randomly get what you want, which is a writable page, and then you're like, got it. So it boots itself, it thinks it's validated, and then you change it, right? Okay. But when you are owning someone else's iPhone, you write an exploit for it, you cannot run shellcode. You have to do everything in ROP, right? The whole payload, top to bottom, your arbitrary code is all written in pieces of code that already exist. And that is not, by any stretch of the imagination, the hard part of owning an iPhone. Once you get to that part where you're like, oh, I just got to build my shellcode out of ROP gadgets, the problem is solved, and you tell your boss you're done, and then you spend 4 months screwing around writing the ROP chain and writing a pretty report for the person who pays you to do it, right? That is not a problem, that is just typing, okay? The distinction here is that a lot of the time when you're doing security research, you don't know if what you're trying to do is possible or not within the time frame you were given, right? You may not find a bug in the time frame you're given. You may not be able to exploit that bug in the time that you're given. But once you get to the ROP chain, it's all over but for the crying, okay? You can do it, and you'll never fail.
Is Secure Boot a form of like fully signed chain?
In what platform?
Like on my laptop. Like if
On
I go through
Windows?
it, no. Like you can do it on Linux. Like if I go through and enable it in the BIOS.
Don't know. I do not know. Does anybody know?
From what I remember, they were just signing various images, and you just had to like register your own public key with the like hardware manufacturer if you were a software person. So you could sign your code, and the TPM can verify that your signature is in the code. I don't think it's a fully signed chain. I think it was just like, okay, this software is from a approved manufacturer. We like this. Okay, here it is. I don't think it verifies. I don't think Secure Boot verifies this technically. It could run on that.
I don't think so. It's not like on page write revalidate.
Yeah.
So there's a difference in the way that these things work fundamentally, and that is if you can add a key to your own system, it's not a fully signed chain. Okay, and the reason that is because if I can take my iPhone and add my own key and put my own driver on here, now I can put a debugger on my own iPhone. If I put a debugger on my own iPhone, I can write the exploit to own your iPhone.
Right.
And their vested interest is in not letting you run anything that they don't want you to run on it. And so it is whether you control it or the company controls it that makes this difference, right?
Okay. I have some.
Sorry.
I was to say I have some vague memory of seeing a talk with someone like set up some like secure chain on their laptop, and then they wrote like a signer into like the initial like boot sector, and then like blew a fuse that way it would never be overwritten.
So you would use that if you had your own laptop that was encrypted and you were going to take it to some country through customs and did not want them to break your encryption. Without the fully signed chain, they can flash the chips that load your crypto decryption with something that will store your key when you type it in. Does that make sense? Yeah. So do you own it or does somebody else own it?
So if a chain isn't like, fully signed or fully secure, is that how you can jailbreak your phone or?
So they are still fully signed and you are not breaking that. You never break the sign chain on a device like this. What you do is you get control of EIP, but you never write a page that stores data that hasn't been signed. You just make use of pieces of signed code, right? You can write a ROP chain and never have to write executable pages, right? And that's the thing. Every page that is marked executable is validated as being signed, right? So you can't run arbitrary shellcode, but you can run arbitrary code, right?
So if you're trying to, exploit an iPhone, let's go to a page, like you eventually jump to a page that is verified as executable, and then you can run code on that.
The same way you did when you did jump ESP in your exploit, the same way you did when you did call system, right? You're calling code that already exists. That's signed and valid. It wasn't meant to be run in that order, right? But it was meant to be run. Okay. So that's the difference there. Okay. All right, so what are the two ways that we can do that are very simple in this case? The simplest is mprotect. Mprotect changes the protections on a page. It's a syscall that does it. There's a function in libc. That's what I showed you in both of those chains. It is your page, which must be page aligned. That means 1,000 bytes aligned. It is your size of memory, also page size, so in increments of 1,000 hex bytes, right? That's the size of the page, 4096 decimal 1,000 hex. And then the protection you want, which is going to be 7D for, I'm sorry, no, that's the syscall. The protection you want is probably 7, just like for chmod. And so in the example of AV01, if the stack was not executable, what I would do is I would mask the bottom bytes of ESP off. So I would be like, I would be like ESP and FF, FOOO. So if you AND it with that, you cut off whatever is there and you maintain whatever's here, and that masks off and says, all right, show me the start of the page that ESP is pointing to right now. And then you'll give it a size of 1,000 bytes, or just to be safe, 2 pages. And then you will give it your proper protection. And then what you will see is if you look at your page mappings before and after you do this, the first time you look at it, you'll see 1 entry for the stack, and it'll say read write. And then immediately after you call mprotect, there will be 2 entries for the stack. All the other pages that are on the stack, and then your 2 pages, read write execute. That proc map will change instantly, and you can check it before and after to know that you called mprotect correctly, okay? Pro tip for validating your chain there. And so then the next thing you do is, after you've done that mprotect, where would I like to return after that? If I put my shellcode right after the ROP chain, it's your best friend, the gadget that you have used so many times before. .bsp. Right? So mprotect ROP chain, shellcode. Mprotect, .bsp, and then here's EVP and buff. Right? So you're right here. This is where ret used to be. It's the start of your ROP chain. You go to the end of your ROP chain, you write your shellcode right after it, you say jump ESP, now it's executable. Bob's your uncle. I don't know why British people say that. Anybody knows, tell me after class. Okay, so that's the first one. 1 and done, you call 1 function, you're good. Second one, if you want to stage a little bit, is to mmap a whole new page, read, write, execute, and then copy your shellcode to the new page, right? You're going to have to do a little bit more math here with ESP to find where your page is, which means you need to know how long your ROP chain is, provided you put your shellcode right after it, and add to ESP, or add something to ESP, store in another register, use that. You will have to make use of the return value of mmap to know where to copy memcopy to. So doing this one, you actually have to juggle a couple values, right? Normally what you would want to do is just push them onto the stack, but that's not going to work in this case. So it would behoove you to make a data store that you reference from a register like RDI or RSI and build a structure there, right? Just like you build a structure in C to store data you want, you would say, okay, so ESP minus 200, that's way outside of what I'm going to use here probably. I'll put a structure there that I understand the structure of, and I'll store the return from mmap. I'll store where my shellcode is pieces in that structure, and I'll reference them later in my ROP chain, right? Make them easily referenceable from a single register, so it would be like That is your shellcode address, which you may find by any of the methods we discussed already. And then RDI +4 is going to store your mmap value, map return value. And then you can just reference them from RDI later in your ROP chain or shellcode. In Windows, this is almost a necessity to create and carry along this structure with you. If you're doing a local, you're going to resolve all of your functions and gadgets and send them along in this structure with your shellcode and reference it from your shellcode. What's up?
I have a question. When we do unprotect, do we override return with the address of unprotect in GOT table?
No, you don't have to mess with the global offset table at all. When you are building this ROP chain, when you call ret, whatever the next thing on the stack is, that's what ESP is going to be pointed to. It's going to pop that value off the stack, and then it's going to start executing there, right? So instead of calling functions in the way that you're normally used to, you're going to use them as return addresses, right? Just like you use jump ESP, pretend jump ESP is a whole function. You don't call it, you just return there, right? Knowing that ret does just two things, pop ESP, move that value into EIP, you just use it like that. Instead of using it in the way that it's intended, you just use it to control EIP. And so you control EIP over and over and over again. And you just put stuff in the way so that it happens to work out that everything the function thinks it's going to need is there and removed properly.
Is there a reason to manually go through like all the trouble to get full read-write execute permissions and then jump to your shellcode instead of just manually building the shellcode with gadgets?
Yeah, because it takes you way, way longer to manually build your shellcode with gadgets. And it's much larger, right? So when we wrote our shellcode, what's the smallest shellcode you guys use? Like an 18 hex byte shellcode, right? Is that about?
I've seen 18 before, yeah.
Okay, so how many, 18 hex bytes is 1, 2, 3, 4, 5, 6 return values, right? So you could probably fit most of this and definitely all of this plus some in those 18 bytes. Now on an iPhone or a PlayStation or an Xbox, you're going to have to do that, but it's always easier to just gain arbitrary execution. The other thing is arbitrary execution is going to run a lot faster for you. So if you are racing to fix a structure up that the program needs to run, perhaps using another thread, like the heap, and you need to do that fast, you want to do that. You notice one of the chains that is not up here is spawn a new thread with your shellcode. If you want to spawn a new thread with your shellcode, you should do that in the shellcode. Get the execution first, then spawn the new thread, right? Other reasons. When you write one of these things, you are generally not the operator. Right? There is a separation of work in the world where some people specialize in one thing and some people specialize in the other. We are not talking about operations in this class because people that write exploits are not operators anymore, unless you're a freedom fighter. And even then, you're probably not. Like if I were to do this and try to hack someone, I have friends that are operators. So I would say, hey, come work with me. I'll feed you these bugs and you be the operator, right? And what that means is that operator is going to pick different shellcode based on their needs in the operational environment. And so we don't want to hard code pieces of shellcode into our exploit. We want our exploit to be as modular as possible, right? And that means being able to plug in arbitrary shellcode based on the operator's needs at runtime. Just like Metasploit lets you do. Does anybody here use Metasploit? I suggest you go use Metasploit. Just mess with it locally on your own computer on a VM so that CSRF does not call me up to say that one of my students tried to own something else outside of their own computer. But mess with it so that you can see what is split apart in the exploit, what you can pick at runtime to suit your need at the time, right? So that's the main reason, is you go hand this off to somebody else with a report that says, this is how you use this thing, this is how you customize this thing, this is how you integrate this thing into your framework. And so that means being able to change out what it actually does. All right. A lot of people think you need to have some amazing tool to hunt for gadgets, to find the pieces of code you need. What kind of an amazing tool do you need to find FFE4? It's grep. There is a search function in your debugger. There is a search function in your disassembler. You load libc up into IDA or Ghidra or Binja or whatever the other 3 weird ones you guys use are. And you say search FFE4. There it is, done, write it down, right? What if I want something more complicated? Oh, I'll search 89E3C3. It's gonna be there. It's definitely gonna be there, right? For any piece of a normal shellcode, you do not need any tools. You can just look. Everything's small, you have a search function. There's only one problem, okay? In the cases that we have been looking at, you control the stack. You already control the stack. Great. So ESP is already pointing exactly where you need it to go. So if you can write right after ret, like in the ABO1 case, not in the homework example 2 case, but in the ABO1 case, you're fine. You just write it right where ret is. That's where you start your ROP chain, and it's just going to go, okay? In a more complicated case, maybe you have like a sub-ESP ret where you move it back down into the bottom of your buffer, and that's where your ROP chain is if you can't write arbitrarily up, right? So your first chain says move ESP here, okay, now pop the next ret off. So you're just subbing it back into a space you control on the stack. Extremely easy to find. Sub-ESP ret is going to be everywhere. You're going to find it, okay? Nowadays, if you are not writing a stack exploit, your data is not going to be on the stack. And at the time that you gain execution, it's not going to be running return. It's going to be calling a function pointer. You'll almost always, in modern cases for high-end targets, be doing vtable shenanigans. A heap overflow or a use after free or something of that nature. And so what that means is you don't have control of the stack. ESP is pointing on the stack, your data is way F over here, okay? But ECX is pointing at that object. If you had that thing called, that's the thing calling the method, that's the thing that's corrupted, ECX is already pointing there, right? It's the this pointer on your C++ class. And so very often, if you can do this, 89cc C3, you're still good to go. That is your simplest, what we call stack pivot. Okay, you are moving ESP from where it normally lives on the pages that the loader has allocated for the stack. You're pointing it at a place that you control that data. That's a stack pivot. That's the simplest stack pivot. It often works. Sometimes it gets complicated. Okay? And that is the time when you actually do need a tool to solve the problem for you. Okay? So, if you do need a tool to solve the problem for you, I got 3 minutes to tell you about it. Let's go fast. You do 2 things. The first is you get a list of all of the gadgets in whatever module you can get a peek in. There will be a module that is easiest for you to find the base address of using some other bug. Okay? That's our peek. We know where one module is. You take that module, you do this to it. You search for every C3, C2 jump instruction. And then you start walking backwards. Okay? And so you pick what n is in this case, and there's like a mostly efficient way to do that, and I think the number is something like 15. So you'll say C3 is my first byte. What byte is before that? It's FF. Okay? That's one gadget. Store it in a database. Okay? Step back again. It's 8.3. That's another gadget. Store this whole thing in a database. Step back again. You do this n times. Okay? So you're going to start with 2 bytes because this is your 1. So between 2 and n, You just keep going up until you hit whatever n is, probably 15. For every C3, for every branch instruction on the thing, and you store that in a database. Once you have that, that's all the possible gadgets from that module, okay? And then you use a solver to figure out which one does what you want.